Hey there, awesome physics students. I want to do two examples of motion diagrams and how they connect with the second law. So for the first example here, let's imagine that you're in a car and you're traveling and you hit the brake and you're slowing down. And so your displacement over equal time intervals reduces. And so if you think about your velocity vectors through each of these, so this is like the initial velocity, this is the final velocity. Let's find the change in velocity, or the delta v vector for this motion here. So remember, delta v is v final minus v initial as a vector. So we want to take v final, that's this one, and then subtract v initial, so that's add a negative v initial. And remember, we start where we start and we end where we end. We end here, so that means the delta v points that way. Acceleration, of course, is delta v over delta t. So the acceleration vector points in the same direction as delta v, and therefore the acceleration points that way. All right, that's nice. We've done this before, but then let's think about the free body diagram for the car. If you're traveling, let's say you're traveling this way with the velocity like that, what are the forces on the car? Well, the car is touching the ground, so there's going to be a normal force straight up, perpendicular to the surface. Then there's going to be the gravitational force because it's on Earth. And let's think about, how do the tires interact with the road because they're touching the road? There's going to be some friction, and that is how car tires speed your car up or slow your car down, as they interact with the road through friction. In this case, the frictional force is going to point that way to slow you down, and that's static friction. And so if you look at the net force, if you add these three forces together, right, you take the normal force and then you add to that gravitational force, those two will sum to zero, and then you'll be left with the frictional force. And so this tells you that the net force must point to the left here, which is completely consistent with the acceleration. All right, those two forces, because of the second law, those two have to always, always, always point in the same direction, and that's consistent with our delta v direction as well. Let's do another example. Imagine that you throw a projectile up in the air, and it goes up to some peak height. Let's say you throw a soccer ball or something like that, and it comes back down to the earth here. So the motion as it's traveling through the air, this is in free fall. So let's say this is let's take these 2 points. This is v initial and v final. And we want to find delta v. So we take v final and we add to that v initial. So we flip the direction of v initial and add it to the end here. And so this is negative v initial. And therefore delta v starts where we start and ends where we end. So delta v points down, directly down. And this tells us then the acceleration vector must also be down for the same reasons we talked about right here. Well, what about the free body diagram? How is that consistent? Well, while the object is in the air, what are the forces acting on it? It's not touching anything. There's no ropes. It's not sliding. The only force that's on it is gravity. So the net force then will point straight down. And this is completely consistent with the acceleration vector. So in this case, I'm working from the motion to predict which way the net force vector points. But we can also do it the other way. We can use the free body diagrams to find the net force and then use that to predict the acceleration vector, which will then tell us how the velocity will change.